the logic in the logic in the mean value in the intermediate value theorem, sorry, here is that telling us that if a function is continuous, of course if a function is continuous, we know that it does not skip any value. Now, if a function does not skip any value in turning from negative to positive, that means that one of the values it did not skip is a 0. And therefore, we are sure that if a function is continuous here, and then at one point it has positive values on that interval, and then it also has a negative value, okay, then we are sure that one of the values it did not skip is the 0. That means that we are sure that the root actually does what? Exists. So the key in this theorem here is that 1, the function is continuous, therefore we know that it does not skip any value, and it is positive on that interval and negative, positive on the interval and negative on the same interval, like it has different signs, okay, on that interval. Then at least we know that the root lies between that interval, okay. Now we can describe the method here in detail, okay. We'll describe the method in detail here. That suppose we want to find a solution of to the equation f of x equals to 0, where f is continuous, okay, and then given that f is continuous on the given interval here, which is a0, b0, okay, if it satisfies that f of a0 times f of b0 is less than 0, i.e., remember we said that this means that they have different signs, then we are sure that the root exists between a and b, and we get this root by computing, we get this root x0, okay, we get that root x0 by computing 1/2 of a0 plus b0, okay. All right, let us do this here. Let us do this. So we have, let me draw a straight line here. Okay, so we have an interval here. All right. Okay, we have an interval, and then we have our starting value a0. I mean the interval a0 and b0, closed interval a0, b0, okay. So we computed f of a0 and computed f of b0, and we found that they have different signs. Then the root here, x0, we have said we simply compute 1/2 of a0 plus b0. That is the bisection, okay. That is x0. So the next root, x1, we are going to check for two things, okay. One, now the next root x1 could lie in either this interval here. You agree that it could either lie in this interval a0, x0, or that is this interval here, or it could lie in this other interval here, x0, b0. Now, to check where it lies, we will compute x0. So we will compute f of a0 times f of x0. So if these are of different signs, i.e. less than 0, then we know that the root lies in this interval here. And if the root lies in this interval, of course we now get the next approximation. Okay, if the root lies in this interval here, so we know that now our a1, okay, on the next interval we are going to look at is going to be equal to, we set it to be a0, and then our b0, sorry, our b1, we set it to be x0, this value we have here, i.e. we are now looking for the next approximation. We are looking for x1 in the interval defined by a1 and b1, but a1 we set it to be a naught. It is the same value because we have checked that f of a naught times f of x naught is less than 0. Therefore we are sure that the root lies in here. Therefore on our new interval here, which is a naught x naught, which we are going to define by a1, we shall set a1 to be this same value here, and now our b1 is going to be this value for x naught, which we computed here. All right. Else, if this was not true, and it was true that f of x naught times f of b naught is what was less than 0 here, okay, then we are sure that the interval now lies in this interval here, this one here, because f of x naught and f of b naught are of different signs. If that was the case, then that means that we would look for our next x1, okay, the next approximation in this interval here, this one here, between x naught and b naught. So that means that we would set our a1, okay, to be this value here, x naught, and then we would set our b1 to be now this value here, which is b naught. In other words, you would look for x1 in this new interval b1, I mean a1 b1, where this is equal to x naught, the value we computed here, and b1 is equal to b naught, the original value we had here. Otherwise, I said that if it was in this interval, if we had found out that it is f of a naught times f of x naught, which is less than 0, i.e. of different signs, then that means that we would look for a1 b1 within this interval, where our a1 is the same here, a naught, and then our b1 is this value here, the end value here, which is x naught. Okay, so wherever it would have taken us, if it had taken us here, then now we would look for okay, now if it had taken us here, then we would find that x1 is going to be equal to 1/2 of a1 plus b1, which would be equal to 1/2 of a1. We already know it, we said it is our a naught, which we already have, and then b1, we computed the value of x naught here because we said b1 is equal to x naught, so plus x naught. Otherwise, if it was this side, then we would have that x1 is equal to 1/2 of a1 plus b1, where we know that this is 1/2 of a1 is our x naught, and then our b1 is our b naught. Okay, so we just continue making, checking where is the root lying by checking the signs of, the end of this interval, and then if we are sure that the root lies there, then we bisect. Then we check again where the root lies. If we have found out that the root lies in there, then we bisect, and then we continue on and on and on. So I hope this is easily understood. If it is not, then we are going to try out an example in the next video. Okay, thank you so much.